We all love pretty colors. Maybe your favorite one is blue, or green, or red. Perhaps you enjoy the whiteness of snow or a colorful sunset. But the beautiful colors you see, the ones your eyes can process, aren't just there for looks. What I mean is, while we can use colors to code or classify things like a terror alert system or to indicate our mood, we can also use them to gauge the temperature of a distant star as well. It's true, and this lesson will tell you how. What color is the light emitted by the sun? If you look up in the middle of the day, you might say something like white or yellow. Later, during sunset, you might tell me it's red. The real answer is that the sunlight is a mixture of a lot of different colors, all of the ones we just went over and lots more. If you've ever used the prism to make a rainbow out of sunlight, you created a spectrum, an arrangement of light according to a wavelength, in this case of visible light. It used to be thought that the prism actually added color to the white light, but Newton disproved this when he placed another prism to just one of the colors of the rainbow created by the first prism. Since the color remained unchanged by the second prism, this proved that the original sunlight was separated out into different colors and no color was added to it. But there's something even more interesting going on here than what meets the eye. British astronomer William Herschel also passed sunlight through a prism, just like Newton, but he held a thermometer just beyond where the red end of the visible spectrum was. To his amazement, the temperature increased. What does this mean? It means that visible light is only one part of something much bigger. That bigger thing is called the electromagnetic spectrum, and it includes all the different forms of electromagnetic radiation, or energy, which includes visible light. The electromagnetic spectrum is split up not by true color, as per our prism example before, but by wavelength or frequency. The simplest way an object can produce more light is by increasing its temperature. For example, a light bulb's filament emits light because the electrical energy the light bulb uses causes its filament to go up to a very high temperature. The hotter an object, the brighter it becomes. Hotter objects emit most of their energy at shorter wavelengths. Conversely, colder objects emit little energy. The wavelengths of light of maximal intensity in colder objects tend to be that of longer wavelengths. But because stars emit a lot of different wavelengths of light, we need a way to determine how much, proportionally speaking, each different wavelength of light is being emitted. One way to do this is to make a black body curve. A graph that plots wavelength versus intensity of light thanks to data gleaned from specialized cameras. A black body is a theoretically perfect radiator. In such a curve, as the temperature of an object changes, so does the graph of the spectrum. A higher temperature would have a graph where the peak of the curve is located at shorter wavelengths, and vice versa for a colder temperature. This notion is known as Wien's law, and it can be boiled down to this. The wavelength of maximum intensity that a black body emits is inversely proportional to its temperature. The hotter the temperature, the shorter the wavelength at which a hot star emits its maximum radiation. The reverse is true as well. Knowing all of this, we can see, using the graph on the screen, that objects with lower temperatures like 3000 Kelvin peak at a wavelength of about 1000 nanometers. This is beyond the visible spectrum of light, in infrared territory. But the object isn't invisible. As you can see, the curve encompasses plenty of visible light. However, because the peak is skewed toward the longer wavelength side of visible light, a lower temperature object will appear red in color because it emits more red light than blue light. On the flip side, an object that has a temperature of 12,000 Kelvin has a peak of maximal intensity at a wavelength shorter than visible light, in ultraviolet territory. Once again, the star isn't actually invisible to us because the curve clearly includes the wavelengths visible to the human eye. Not only that, but because the object is so hot, the visible light is very intense. Just look at the peak of that curve compared to the lowly 3000 Kelvin one. This means our 12,000 Kelvin object will glow very brightly at every wavelength precisely because it's so hot. But because the curve is skewed toward the short wavelength side of visible light, it will glow a blue color as opposed to a red one. So, to summarize, if a star is a brilliant blue color, it's really hot and emits a lot of energy. If it's red, it has a cool surface temperature instead. Therefore, the dominant wavelength of a star's light can tell us its surface temperature.
A spectrum is an arrangement of light according to wavelength.
Visible light is just one small part of the entire electromagnetic spectrum, which has different forms of radiation based on different wavelengths or frequencies. The hotter an object, the brighter it becomes. Hotter objects emit most of their energy at shorter wavelengths. Conversely, colder objects emit little energy and the wavelengths are longer. To determine how much, proportionately, each different wavelength of light is being emitted by a star, and thus its temperature, we can use a black-body curve, a graph that plots wavelength versus intensity of light that we get thanks to data gleaned from specialized cameras. A black body, by the way, is a theoretically perfect radiator. The relationship shown by the curve, known as Dean's law, can be boiled down to this. The wavelength of maximum intensity that a black body emits is inversely proportional to its temperature. This means that hotter stars tend to be blue in color, and cooler stars are red in color.